Hello everyone, welcome to Aryan Tutorials. So in this video, we are going to discuss how to derive an expression for the loss of head or energy due to the friction. Okay, whenever the fluid is flowing through a pipe, so loss of energy takes place due to the frictional resistance offered by the internal surface of the pipe. So what is the amount of the loss is taking place? So that amount of the loss we can find out by using an expression. So that expression we are going to derive now. So for that I want to consider a uniform horizontal pipe which is having certain particular diameter d. Okay, assume this is as a pipe through which the flow of the fluid is taking place. So for this pipe I want to consider two sections, 1 and 2. The distance, that is length of the pipe in between two sections, I want to assume as L. Okay, at section 1 I want to assume pressure as P1 which is acting in the direction of the motion of the fluid, and at section 2 I want to assume the pressure as P2 which is acting opposite to the direction of the flow, which will be causing the reduction in the pressure during the flow of the fluid through the pipe. Okay, and here the internal surface can offer certain frictional resistance. That frictional resistive force I want to assume as F1. Okay, and next I want to assume as the velocity as v1 at section 1 and velocity as v2 at section 2. Okay, and the area of pipe is A, which is constant throughout the pipe. Okay, so in between these two sections I have assumed two conditions. Okay, so by analyzing these two conditions for the flow of the fluid through the pipe, we can derive the expression for the loss of head or loss of energy due to the friction. So first thing I want to apply Bernoulli's equation. Okay, first I want to apply Bernoulli's equation. I want to apply Bernoulli's equation for the two sections. Okay, for the two sections I want to apply Bernoulli's equation, which states that the total energy, whatever the total energy available at section 1 should be equal to total energy at section 2. Okay, so according to the Bernoulli's equation we can state that whatever the sum of the energies we are having at a particular point should be equal to the sum of the energies at the second point when the pipe is extremely smooth. Okay, when there is no loss is taking place, but here the loss of energy is taking place due to the friction. Okay, so that loss of energy I want to assume. Okay, I want to assume loss of energy as HF. I want to assume loss of energy as HF. Okay, this amount of the loss is taking place. So here whatever the energy available at section 1 cannot be equal to energy available at section 2 because of this much of the energy loss we are getting in the form of the head. Okay, so to make them the equal, that means to make the total energy available at section 2 equal to the section 1, we need to add whatever the loss of energy is taking place. Okay, now whatever the energy we lost, if we add that amount to the energy available at section 2 after moving from 1 to 2, we will be getting the value equal to the energy available at section 1. Okay, so according to the Bernoulli's equation we can write it as total energy at section 1 is equal to total energy at section 2 plus whatever the amount of the lost we got according to the flow of the fluid from 1 to 2. Okay, so according to the Bernoulli's equation the total energy can be written as, again I want to write it as P1 by rho g at section 1 plus and V1 square by 2g plus Z1 is equal to, again we can write it as P2 by rho g at section 2, that is plus V2 square by 2g plus Z2 and the energy lost HF. Okay, so this is the equation we can write according to the Bernoulli's equation already we know. Okay, and again here due to the same cross-sectional area, we are using the same cross-sectional area pipe with the constant diameter, so in that case we can write it as whatever the velocity at section 1 can be equal to velocity at section 2. Similarly, I want to assume a datum line. If you assume any datum line below the pipe, because of it is a horizontal pipe, and again height of the center from the datum line can be equal to the height of the center of the pipe from the datum line for the section 1 and section 2. So again z1 and z2 becomes equal to same. Okay, so this v1 square by 2, v2 square by 2 gets cancels. Okay, according to the conditions we got, this one get cancels, and this one get cancels. So finally the modified equation will be getting p1 by rho g is equal to p2 by rho g plus hf. So I want to take p2 by rho g to the left side. So now we can write it as p1 by rho g minus p2 by rho g is equal to hf. Okay, after taking rho g as common, we can write the equation as p1 minus p2 is equal to rho g hf. Okay, so we can write the equation like this after modifying according to the conditions we have assumed. Okay, so assume this equation as 1. Okay, next I want to go for what is the frictional resistance. Here we are saying that due to the motion of the fluid from section 1 to section 2, certain loss of energy is taking place, which is causing the reduction in the pressure value. Okay, and at the center of the pipe the velocity will be maintained same. And here I want to write the what is the frictional resistance. Okay, now so this f1 what I want to write. So the frictional resistance f1 can be written as, we have certain standard formula. Okay, that standard formula you should remember. Okay, that standard formula is whatever the frictional resistance frictional frictional resistance per acting per unit wetted area in sorry again per velocity into wetted area into velocity square. Okay, this frictional resistance, the formula is for finding the frictional force, that is the resistive force offered by the internal surface to the fluid, can be written as frictional resistance per unit wetted area per unit velocity. This is also per unit velocity into wetted area into velocity square. Okay, by this formula we can write the frictional resistive force. Okay, so f1 is equal to, I want to write, so this entire time I want to assume as f dash, which is the frictional resistance per unit wetted area per unit velocity into wetted area. So what is the wetted area? Wetted area means whatever the liquid is in contact with the pipe. So that means liquid is in contact with the internal surface of the pipe. So wetted area means we need to consider what is the surface area of the pipe which is covering at a particular distance of L. So that area can be obtained by circumference of the pipe into length of the pipe, after which we are considering the flow of the liquid through the pipe. Okay, that is the unit wetted area into as it is velocity square. Okay, so this f1 again can be written as f dash into pi d is the perimeter, we can write it as circumference, or perimeter we can call it as. So perimeter into L into v square we can write it as. So f1, the resistive force, we got it as f dash into perimeter into L into v square. So again keep this equation aside. Okay, this equation, keep this equation aside. Okay, now I want to write what are the forces are acting. One force already we have written, which is the frictional force, and next another force I want to write, the force acting at section 1. Force at section 1 I want to write. So what is the force acting at section 1? Which is due to the pressure P1. So the force due to pressure at section 1 can be written as P1 into area, because pressure is equal to force by area. So force is equal to pressure into area. Similarly, I want to write what is the force at section 2. So again, which is also due to the pressure, that is I want to write it as P2 into A. Okay, so again already we have written the force, that which is the frictional force, that is the frictional resistance. Okay, frictional force acting on the fluid when it is flowing from 1 to 2, that is Fn. Okay, so here we will be assuming the flow as a steady state flow. Okay, the flow is taking place through the pipe is steady state flow. Okay, so in that steady state flow condition, that means we can consider as a equilibrium condition. Okay, so in that steady state flow, sum of forces in the direction of the flow. Sum of forces in the direction of the flow can be equal to 0 according to the steady state condition. Okay, this condition will apply for the forces acting on the fluid. So what happens, let us see. Okay, I want to erase this one. If you want to note down, please stop the video and note down. So I'm going to erase this. Okay, so now I want to write some of the forces. So what are the forces we have considered already? Pressure force acting at section 1, pressure force at section 2, and the frictional force. Okay, so the sum of means we need to take according to the direction of the flow. So in the direction of the flow we'll consider positive, that is P1 into A, and opposite to the direction of the flow, which is minus P2 into A, and again the frictional force is opposite to the direction of flow, minus F1 is equal to 0. Okay, so I want to write it as P1 minus P2 into area. We can take the area as common, which is equal to, we can write it as F1 again. Okay, so again I want to write P1 minus P2 is equal to F1 by A. So F1 already we got the formula as F dash into something, so that we try to write it as F dash into P perimeter into L into V square by A. Okay, this is the equation we got. Once again P1 minus P2. So assume this equation as 2 again. Okay, assume this equation as 2 again. Okay, so P1 minus P2 is equal to one formula, P1 minus P2 is equal to one formula. So we can make these two equations equal now. So I want to make these two equations equal for getting the expression for the loss of head due to friction. So I want to erase this one. Okay, so from 1 and 2 I want to write from 1 and 2 both should be equal. 1 is equal to 2, so we can write it as rho g h f is equal to f dash into p perimeter into L into V square by A. Okay, and again I want to write hf, which is the required loss of head due to friction. That is, I want to write it as f dash by rho g into P by A into L into V square. Okay, this is some sort of expression for the loss of head due to friction. Again we can modify this equation. So how can we modify? And again let us see here how can we modify further for getting the simplified equation for the loss of head due to friction. Okay, for the flow of the fluid. So how can we modify? Means first I want to take perimeter by area. So I want to take perimeter by area. So perimeter formula already we know, pi d, and the area is pi d square by 4. So pi gets cancels, and from d square 1d gets cancels. So finally we'll be getting 4 by d. Keep aside. Again I want to take another thing. Take f dash by rho. So both are constant only. So f dash is constant and rho is constant. So when you take this rho ratio, we'll be getting the value is half of the coefficient of friction, f by 2. So this f dash by rho can be equal to f by 2, which is the half of the coefficient of the friction. Okay, so for p by a, f dash by rho, we got new terms according to the empirical relation and the modification of the p by a. Okay, this is an empirical relation. Okay, so I want to substitute this in hf. Okay, and further that I'm going to erase in this one. So I want to erase totally. Okay, if you want to note down, please stop the video from starting and try to note down whatever I'm explaining here. So I want to substitute these two in this equation again. So hf is equal to, can be written as hf is equal to, or can we write as f dash by rho, already we got it as f by 2, already g is there, so 2g into p by a can be written as 4 by d into L into V square. Okay, finally we can write it as 4FL V square by 2GD. So this is the equation which represents loss of head due to the friction. Okay, don't cancel 2 2 4 2 2 ja 2 2 2 ja 4. Okay, so this form of the equation is called as, sorry, this form of the equation is called as Darcy's Weisbach equation. Okay, so the above format whatever we got, so that equation is called as Darcy, because it is derived by the Darcy Weisbach, okay, according to the laws given by the William Froude. So which is the equation is called as Darcy's Weisbach equation. Okay, so sometimes this equation again can be written as HF is equal to only FLV square by 2GD. Okay, so by neglecting the 4, again this equation can be written as FLV square by 2GD. Okay, so this is the way of deriving an expression for the loss of energy or loss of head due to the friction taking place for the flow of the fluid, that is the flow of the liquid through the pipe. Okay, here again go through the terms. F is the coefficient of friction, L is the length of the pipe, V is the velocity, and G is the gravitational acceleration, and D is the diameter of the pipe. Okay, so I hope you understand this one. If you still have any doubts, please feel free to give a comment to my video, and I'll try to clarify your doubts. And don't forget to subscribe to my channel. Once again, thanks for watching my video.